Title of today's module is Polynomial Rings. Dear learners, today we are going to discuss about polynomial rings. We will see the concept of a polynomial. What does the term polynomial mean to us? We think of algebraic expression such as 2x plus 1, 3x square plus 7x minus 1 and 6x cube plus 5x square plus x plus 9, etc. We speak of this as being polynomials in x and say that 2x plus 1 has degree 1. 3x square plus 7x minus 1 has degree 2 and 6x cube plus 5x square plus x plus 9 has degree 3. The polynomials of degrees 1, 2, 3 are sometimes called as linear, quadratic or cube respectively. We know how to add, subtract and multiply such polynomials. Let's see the addition of two polynomials. Take these equations 3x square plus 7x minus 1 plus 3x plus 7. 3x square plus the coefficient of x are 7 and 3. So 7 plus 3 is equal to 10 is equal to 10x and plus 7 minus 1 is equal to 6. So the answer is 3x square plus 10x plus 6. Let's see the subtraction of two polynomials. Take these equations 3x square plus 7x minus 1. The next one is 3x plus 7. We will subtract 3x square plus 7x minus 1 minus 3x plus 7. Here the coefficient of x square in the next equation, the second equation is 0. In the first equation it's 3. So 3 minus 0 is 3. So it's 3x square. The next we will see the coefficient of x. It's here 7x. In the second equation it's minus 3. So 7 minus 3 is equal to 4. Here it's minus 1. Already there is 7. So minus 7. So minus 7 minus 1 is equal to minus 8. Next we see the multiplication of two polynomials. 3x square plus 7x minus 1 into 3x plus 7. So now we are multiplying 3x square into 3x plus 7 plus 7x into 3x plus 7 minus 1 into 3x plus 7. So we will get the answer 9x cube plus 21x square plus 21x square plus 49x minus 3x minus 7. Now we will simplify it. So we will get the answer is 9x cube plus 42x square plus 46x minus 7. The collection all of such polynomials form a ring called polynomial ring. Let O be any ring, a polynomial f of x with coefficients in R. The symbol x is usually called an indeterminate. For the present, we shall assume that x is not in any algebraic system and the symbol x is used only in a formal way. We now construct a ring which contains a ring R with indeterminate x. Now, let us see the proper definition of it. The definition is, let O be a ring, a polynomial f of x with coefficients in R is defined to be an expression of the form a0 plus a1x plus and so on an x power n, where n is a positive integer and a0, a1 and so on an in R. AR is called the coefficient of x power r and AR x power n is called the term of the polynomial. The set of all polynomials with coefficients in R is denoted by R of x. Here x, x square and so on x power n are merely symbols. We should not think of x power r as x multiplied by itself or times, since r are not member of any algebraic system and no multiplication is defined for x. Further, AR x power n is not a product of AR and x power n. In the polynomial f of x is equal to a0 plus a1x plus and so on an x power n if sum ai is equal to 1. We drop the coefficient ai from the formal sum. For example, the polynomial 3 plus x in z of x is the same as the polynomial 3 plus 1 dot x. Also, if any coefficient ai is equal to 0, we omit the term ai x power I from the formal sum. For example, the polynomial 0 plus 3x plus 0x square minus x cube is written as 3x minus x cube. Thus, 0, 3, x square plus x cube are all polynomials in z of x. Some examples for the rings of polynomials are the set of polynomials with rational coefficients q of x with 0x is equal to 0 and 1x is equal to 1 is a ring since q is a field. C of x represents the polynomials with complex coefficients and R of x the polynomials with real coefficients are rings. Note that q of x is the subset of R of x is the subset of C of x. The polynomial ring is the 2 of x consists of all polynomials whose coefficients are all either 0 or 1. More generally, we can consider the polynomial ring is it P of x where P is a prime number. Let us see some preliminary operations on polynomials, addition and multiplication of two polynomials. Let f of x is equal to a0 plus a1x plus and so on an x power n and g of x is equal to b0 plus b1x plus and so on bn x power m be two polynomials in R of x. Then addition of f of x and g of x defined as f of x plus g of x is equal to a0 plus b0 plus a1 plus b1 into x plus a2 plus b2 into x square plus and so on. Also, multiplication of f of x and g of x defined as f of x into g of x is equal to a0 plus a1x plus and so on plus an x power n into b0 plus b1x plus and so on plus bn x power m is equal to c0 plus c1x plus and so on cm plus n x power m plus n, where c0 is equal to a0 b0, c1 is equal to a0 b1 plus a1 b0 and so on, cr is equal to a0 br plus a1 br minus 1 plus and so on ar b0 and so on, cm plus n is equal to an bm. For our understanding, let us see an example. Let f of x is equal to 1 plus 2x and g of x is equal to 1 plus 3x plus 2x cube be polynomials in Z5 of x. The ring of polynomials over the field is at 5, equipped with addition and multiplication modulo 5. Let us solve some problems here. The first one is calculate f of x plus g of x. The second one is simplify 3f of x minus g of x. The third one is compute f of x, g of x. Let's find the solution now. For the first one, let f of x is equal to 1 plus 2x and g of x equal to 1 plus 3x plus 2x cube in Z5 of x. So, we have to find f of x plus g of x is equal to 1 plus 2x plus 1 plus 3x plus 2x cube. Here 1 plus 1 and we will take the coefficients of x is 2 plus 3 into x plus 2x cube. Now we will apply mod 5 here. So 1 plus 1 is 2. Here 2 plus 3 is 5 is equal to 5. So we are applying mod 5 here. We will divide by 5. We will get the remainder as 0. So 0 into x is 0. So we are not getting the term of x here plus 2x cube. So f of x plus g of x concurrent to 2 plus 2x cube mod 5. Hence, f of x plus g of x is equal to 2 plus 2x cube in Z5 of x. Next, we will simplify 3f of x minus g of x. is equal to 3 into 1 plus 2x minus 1 plus 3x plus 2x cube. Now we will multiply 3 plus 3 into 2x minus 1 minus 3x minus 2x cube. So is equal to 3 plus x plus 4 plus 2x plus 3x cube. 3 plus 4 is equal to 7. We will apply mod 5. So 7 by 5 we will get the remainder as 2. The answer is we will write as 2 here. And 1 plus 2 into x is 3x plus 3x cube. So 3f of x minus g of x is concurrent to 2 plus 3x plus 3x cube mod 5. Hence 3f of x minus g of x is equal to 2 plus 3x plus 3x cube in z5 of x. Next we compute the third problem. F of x g of x is equal to 1 plus 2x into 1 plus 3x plus 2x cube is equal to 1 plus 5x plus 6x square plus 2x cube plus 4x power 4 is equal to 1 plus x square, and the 5x we are applying mod 5. Already we have seen that. So 5 by 5 the remainder is 0. So 0 into x is 0. So the term is not here. 6x square, 6 by 5 the remainder is 1. So 1 into x square is equal to x square, and plus 2x cube plus 4x4 we have applied mod 5 here. Hence f of x g of x is equal to 1 plus x square plus 2x cube plus 4x power 4 in z5 of x. Let us see some definitions related on ring of polynomials. Definition of zero polynomial. We say that f of x belongs to R of x is the zero polynomial whenever f of x equals to 0 plus 0x plus 0x square plus and so on belongs to R of x. Definition of degree and monic polynomial. Let f of x equals to a0 plus a1x plus and so on plus an x power n, where an is not equal to 0, be a non-zero polynomial in R of x. Then the degree of f of x written as degree of f of x. See thus, it will be written like this, is n, and an is called the leading coefficient of f of x. We do not define the degree of the zero polynomial. A polynomial in which the leading coefficient 1 is called as a monic polynomial. For example, the polynomials x plus 2, x power 4 plus 2 x cube plus x plus 7 and x power 5 plus 2 x power 4 plus x plus 18 are monic polynomials. Let us see the definition of constant polynomial. An element of R is called as constant polynomial. Clearly, the degree of a non-zero constant polynomial is 0. Let f of x equals to a0 plus a1x plus and so on plus an x power n, and g of x equals to b0 plus b1x plus and so on plus bn x power m, be two polynomials in R of x. Then f of x and g of x are said to be equal if n is equal to m and ai equals to bi for all I. Now let's see the definition for primitive roots of unity. Primitive roots of unity are roots of unity whose multiplicative order is n. They are the roots of the cyclotomic polynomial. Cyclotomic polynomials are polynomials whose complex roots are primitive roots of unity. For any positive integer n, then nth cyclomatic polynomial pi n of x is given by pi n of x is equal to x minus omega 1 into x minus omega 2 into x minus omega 3 and so on x minus omega t, where omega 1, omega 2, omega 3 and so on omega t are the primitive nth roots of unity. Let's see the definitions of irreducible and reducible. A polynomial p of x belongs to R of x is irreducible over R if it cannot be factored into polynomials in R of x of strictly lower degree. A polynomial p of x belongs to R of x that is not irreducible over R is called as reducible over R. Next, we see the definition of content. The content of a non-zero polynomial f of x equals to a0 plus a1x plus and so on an x power n, where a's are integers, is the greatest common divisor of the integers a0, a1, a2 and so on an, and it's denoted by c of f. Let f of x is equal to a0 plus a1x plus and so on plus an x power n be a non-constant polynomial ring in Z of x. Then f of x is said to be primitive if the GCD of the coefficients a0, a1, a2 and so on an is a unit in Z of x. For example, f of x equals to 4x square plus 9x plus 2 is primitive polynomial in Z of x. Let us see some examples of irreducible and reducible polynomials. The polynomial f of x is equal to 4x square minus 1. It will be factorized as x plus 1 by 2 into x minus 1 by 2. Here 1 by 2 is the rational number, so it's irreducible over q. But we could not factorize as the integers, so it's reducible over z. The polynomial f of x is equal to x square minus 2 is irreducible over q, but reducible over the real numbers r. The polynomial f of x is equal to x square plus 1 is irreducible over z3, but reducible over z5. Determining whether a given polynomial f of x belongs to R of x is irreducible over R may be difficult, but the upcoming test will make our work easier. Now, let's see those tests. First, reducibility tests for degree 2 and 3. Let f be a field if f of x belongs to f of x and degree of f of x is equal to 2 or 3. Then f of x is reducible over f if and only if f of x has a 0 in f. We now give a criterion for determining the irreducibility of a polynomial in Z of x over q. Next, the Einstein criterion. Let f of x is equal to a0 plus a1x plus and so on plus an x power n be a polynomial with integer coefficients. Suppose there exists a prime number p such that p divides a0, p divides a1 and so on, p divides an minus 1, but p does not divide an and p square does not divide a0. Then f of x is irreducible over q. Let us prove this. We first prove that f of x is irreducible in Z of x. Suppose f of x is reducible in Z of x, then f of x equals to b0 plus b1x plus and so on plus br x power r into c0 plus c1x plus and so on plus cs x power s, where bi cj belongs to z, br is not equal to 0, cs is also not equal to 0, r comma s strictly less than n. Therefore, a0 is equal to b0 c0. Now, p square does not divide a0 and p divides a0. Hence, p cannot divide both b0 and c0. Without loss of generality, we assume that p divides c0 and p does not divide b0. Now, an is equal to brcs. Also, p does not divide an. Therefore, P does not divide BR and P does not divide CS. Choose M such that P divides C1, P divides C2 and so on. P divides Cm minus 1 and P does not divide Cm. Clearly, M is less than or equal to S less than or equal to N. Hence, M is strictly less than N. Now, AM is equal to B naught Cm plus B1 Cm minus 1 plus and so on Bm minus 1 Ci for some I where 0 is less than or equal to I less than M. Now, P does not divide B naught Cm. Then, P divides B1 Cm minus 1 plus and so on plus Bm minus 1 Ci. Therefore, P does not divide Am. But P divides Am since M is strictly less than N, which is a contradiction. Therefore, f of x is irreducible in z of x. Now, let f of x is equal to C f1 of x, where f1 of x is primitive in z of x and C is equal to C of f. Clearly, f1 of x is also irreducible in z of x. Since Q is the field of quotient of z of f1 of x is irreducible in Q of x. Therefore, f of x is also irreducible in Q of x, hence proved. Let us discuss some examples here. The first example is, prove that the polynomial f of x is equal to x square plus 8x minus 2 is irreducible over Q. The solution is, given f of x is equal to x square plus 8x minus 2. Here, a0 is equal to minus 2, a1 is equal to 8 and a2 equals to 1. Let p is equal to 2. Clearly, p divides a0, p divides a1, p does not divide a2 and p square does not divide a0. Therefore, by Einstein criterion, f of x is irreducible over Q. Let's see the next example here. Prove that for any prime number p, the polynomial 1 plus x square plus and so on x power p minus 1 is irreducible over Q. The solution is, given the polynomial f of x is equal to 1 plus x square plus and so on plus x power p minus 1, which is equal to x power p minus 1 divided by x minus 1. Now, x plus 1 the whole power p minus 1 divided by x plus 1 minus 1 is equal to x plus 1 the whole power p minus 1 divided by x is equal to x power p minus 1 plus p c1 x power p minus 2 plus and so on plus p. Clearly, this polynomial satisfies Einstein criterion for the prime number p. Therefore, f of x plus 1 is irreducible over Q. Hence, f of x is irreducible over Q. Next is irreducibility of pth cyclotomic polynomials. For any prime p, the pth cyclotomic polynomial pi n of x is equal to x power p minus 1 by x minus 1 is equal to x power p minus 1 plus x power p minus 2 plus and so on plus x plus 1 is irreducible over Q. Algebraic properties of polynomial rings are, let R be any ring, then R of x is a ring. Let's see the proof here. Let R be any ring. Let f of x is equal to a0 plus a1x plus and so on plus an x power n, and g of x is equal to b0 b1x plus and so on plus bm x power m be two polynomials in R of x. Clearly, f of x plus g of x and f of x into g of x are in R of x. The zero element of R of x is the zero polynomial. If f of x equals to a0 plus a1x plus and so on plus an x power n is in R of x, then minus f of x is equal to minus a0 minus a1x and so on minus an x power n is the additive inverse of f of x. Clearly, associative and distributive laws are hold. Hence, R of x is a ring. Note that R of x is called the ring of polynomials with coefficients in R if R is commutative, so also is R of x. If R is a ring with identity, so also is R of x. The set of all constant polynomials in R of x is a subring of R of x and is isomorphic to R. R of x is integral domain if and only if R is an integral domain. Let R be an integral domain. An integral domain is a non-zero commutative ring in which the products of any two non-zero elements is non-zero. It is enough to prove that the product of two non-zero polynomials is again a non-zero polynomial. Let f of x is equal to a0 plus a1x plus and so on plus an x power n, where an is not equal to 0, and g of x is equal to b0 plus b1x plus and so on plus bm x power m, where bm is not equal to 0. Now, f of x into g of x is equal to a0 b0 plus a0 b1 plus a1 b0 into x plus and so on plus an bm x power n plus m. Since R is an integral domain, an bm is not equal to 0. Hence, R of x is an integral domain. Conversely, let R of x is an integral domain. Then R is a subring of R of x and 1 belongs to R. Hence, R is an integral domain. Here note that if R is a field, the R of x is an integral domain. If R is an integral domain and f of x, g of x belongs to R of x, then degree of f of x, g of x is equal to degree of f of x plus degree of g of x. In general, degree of f of x, g of x is less than or equal to degree of f of x plus degree of g of x. If R is a field, then in general, R of x is not a field. Now let's see about division algorithm. The division algorithm says that let f be a field, let f of x and g of x be two polynomials in f of x with g of x is not equal to 0. Then there exist unique polynomials q of x and r of x in f of x such that f of x is equal to q of x, g of x plus r of x, where either r of x is equal to 0 or degree of r of x is strictly less than degree of g of x. The polynomials q of x and r of x in the division algorithm are called the quotient and remainder in the division of f of x by g of x. When the ring of coefficients of a polynomial ring is a field, we can use the long division process to determine the quotient and remainder. The remainder theorem says that let f be a field, a belongs to f and f of x belongs to f of x. Then f of a is the remainder in the division of f of x by x minus a. The factor theorem says that let f be a field, a belongs to f and f of x belongs to f of x. Then a is 0 of f of x if and only if x minus a is a factor of f of x. A polynomial of degree n over a field has at most n zeros counting multiplicity. The product of two primitive polynomials is primitive. We have come to the conclusion of this session. In this session, we have discussed about the polynomial rings briefly. Let us recall it once again. First, we have started this session with the definition and then we apply some arithmetic operations on polynomials. After, we have seen some definitions related to polynomial rings. Moreover, we have discussed some tests to find the irreducible polynomials with some examples. Finally, we finished this session with discussing about the properties of polynomial rings. I hope this content gave a clarification of polynomial rings. Thank you.